So now we're going to talk about the reaction quotient, which is known as Q. Q is going to kind of compare where we are in regards to the equilibrium constant. So the equilibrium constant predicts the reaction in which a reaction will proceed in order to achieve equilibrium. It lets us know, is it product favored, is it reactant favored? And we can calculate the concentrations of reactants and products once equilibrium has been reached. Well, Q is calculated the same as K. It's still got the same format of the products over the reactants, but the concentrations aren't necessarily at equilibrium concentrations. And so what can happen is we compare Q with K and go, oh, we need more product. We're going to proceed to the right. Or, oh, we need more reactant. It's going to shift to the left or go in reverse. Okay, so we have three scenarios. Q can be greater than or less than or equal to K. Now, I want you to kind of think about the form of each of these, and it's products over reactants. So if Q is less than K, then we have too much of in this Q scenario, we have too much reactant, we have too much denominator. And so the forward reaction will proceed, or it'll go to the right until equilibrium is established, until we have enough product, which is in our numerator, and have gotten rid of some of that reactant that was in our denominator. Okay, if Q is equal to K, then we're at equilibrium. Everything's hunky-dory, easy. And if Q is greater than K, well, that means that we've got too much product and not enough reactant, so the reaction will proceed to the left. The reverse reaction will predominate until equilibrium is established. So let's try an example. We have hydrogen iodine forming hydrogen iodide, and it says that K for this reaction at 450 degrees Celsius is 49. So if 0.22 moles of iodine, 0.22 moles of hydrogen, 0.66 moles of HI are put into a 1 liter container, would the system be at equilibrium? And if not, what must occur in order to establish equilibrium? So we're going to write our Q expression. You see it looks just like a Kc expression, except there's a letter Q in front. And then we're going to plug in the values that were given to us. Notice they were all in moles, but we're in a 1 liter container, so if we divide all of those by 1, we get our molarities. Okay, so go ahead, write this down, put this in your calculator, and you should get 9. So that's what Q is equal to. Well, K is 49. So we are significantly below that. That means we have way too much on our denominator and not enough of our numerator. So we need more of our numerator. We need more of our product, so the forward reaction will predominate until equilibrium is reached. Okay. I want you to try this check for understanding, and when you've done it, you can continue with the video. So if we're going to do this, we're going to plug in those values of NO2 and N2O4 into our equilibrium expression, and we get 0.369. Well, 0.369 is greater than our Kc value of 0.21. So that means we have too much in our numerator, not enough in our denominator. Too much product, not enough reactant. So the reverse reaction will be favored, or will predominate until equilibrium is established. Okay, now I'm going to show you a strategy that we call ICE. I'm going to flip over to the document camera in just a sec. And we're going to use this strategy in this unit and in other units as we move forward. So ICE stands for initial, change, and equilibrium. So let's hop over to the document camera. And we've got this. At 700 Kelvin, the equilibrium constant equals 5.1. Find the equilibrium concentrations of all species if 1 mole of each component is mixed into a 2 liter flask. Okay, so what I'm going to do, ICE stands for initial, change, and equilibrium. So I'm going to write my reaction. And I'm going to start out with my initial concentrations. Okay, so each of these, we have 1 mole of each component in a 2-liter flask. So 1 divided by 2 is 1/2, or 0.5. So I have 0.5 molar concentrations of everything. Okay, C is going to be for change. Well, we don't know which way it's going to change. So we're going to go over here, and we're going to write our Q expression. And we're going to put in our products over our reactants. And here, everything has a coefficient of 1, so it's all raised to the first power. And I'm going to put in my initial values to find out. Okay, so hopefully we see that all of that turns into 1. Well, Kc is equal to 5.1. Okay, so Q is less than Kc. So the reaction is going to proceed until we have more of our product. So it's going to proceed right. Well, what that means is that we're going to gain some amount of product and we're going to lose some amount of reactant. And that some amount we're going to call X. So we're going to lose X from our reactants, and we're going to gain X for our products. Now, all of these are a 1-to-1 mole ratio, so it's just 1X that's being gained or lost. If there was a coefficient of 2, then it'd be, for that particular reactant or product, it'd be 2X. Think about it in terms of mole ratio. So our equilibrium concentrations are going to be 0.5 minus X and 0.5 minus X, 0.5 plus X, and 0.5 plus X. Okay. So Kc, which is equal to 5.10, is going to be the same form as this, but I'm going to substitute in these equilibrium concentrations. So there's CO2. There's water, carbon monoxide, and water. Sorry, that was hydrogen. Okay, so I could look at it this way. Okay, and here's where we're going to do some algebra skills. There's a lot of different ways of solving this. Here, let me autofocus this real quick. If you have an Inspire or any sort of other graphing calculator, what might be easiest is to just graph and find the intercept. So, alright, I'm gonna do this on my Inspire. So, add graphs, and f of x equals, so I'm gonna say 5.1, I'm gonna rearrange that initial equation, 5.1 times 0.5 minus x squared. So that'll be my first equation. Okay, and there we graph it. And then I can add in my second equation, which is going to be 0.5 plus x squared. So I hit menu 3, 1, and I'm going to graph this in. So 0.5, notice I'm going to use my parentheses, plus x squared. Alright, so I've got these. So I've got two parabolas, and if you notice, there are two intersections. Now, a note about this. Whatever x is, it can't be negative. Okay, this is going to be a positive value, so that can help you find this. And also, think about this. I'm starting with 0.5, so I can't lose more than 0.5, because then I'd wind up with a negative concentration of something, and we can't destroy matter. So, in order to find the intercept here, I'm going to go Menu, Analyze, which is 6, for intersection. to kind of eyeball it. Okay. You've probably done this on your calculator a lot. Okay, and it's kind of showing up a little bit funny, but x is 0.193. And if I were to find the other x-intercept, or the other intersection, it would actually be greater than 0.5, so that doesn't work. Okay. Well, that's what x is. Now let's actually use this in context of our problem. Our carbon monoxide and our water concentrations are going to be the same. They're both going to be 0.5 minus 0.193. So that'll be 0.407 molar. And my carbon dioxide and hydrogen concentrations will be equal. So 0.5 plus 0.193, 0.693 molar. Okay, let's try another one. At 35 degrees Celsius, the equilibrium constant is 1.6 times 10 to the negative 6. Determine the equilibrium concentrations of all species if 1 mole of NaOCl is placed in a 2-liter flask at the start of the reaction. So I've got my reaction. I'm going to start with I for initial, and I had 1 mole in a 2-liter flask, so that's 0.5. And it says nothing about the other guys, so we had 0 and 0. Okay, so my Kc expression here is going to be products NO squared times chlorine over NOCl. Okay, well, if I have 0 of my product and it's in equilibrium, like I'm going to have some product. So we don't have to do anything fancy of calculating Q here. We know that we're going to lose some of our reactant and we're going to gain our product. But notice with the coefficients here, we have a 2 to 2 mole ratio here, but we have a 2 to 1 mole ratio between NOCl and chlorine. So for every 1 mole of chlorine that's formed, we're actually going to lose 2x of the NOCl and we'll gain 2x of the nitrogen monoxide. So our equilibrium concentrations are going to be 0.5 minus 2x, 2x, and x. Well, Kc is equal to 1.6 times 10 to the negative 6. So I'm going to plug these into my equation. So I have 2x squared times x over 0.5, there's a 5, minus 2x squared equals 1.6 times 10 to the negative 6. Okay. So 2x squared is 4x squared times x, so that's going to be 4x cubed. And then I'm going to shift my denominator. And I'm going to use my calculator just like I did earlier and solve for this. X comes out to be 0.005. So my concentration of NOCl is going to be 0.5 minus 2 of that 0.005, so 0.49. Okay. The concentration of NO is going to be 2 times x, so 0.01. And my concentration of my chlorine is just going to be x, so 0.005. Okay, so here's my equilibrium concentrations. And this should make sense. Look at how small the equilibrium constant is. That means it really just barely proceeds to the right. That this is a very reactant-favored reaction. Okay, here's your third case. Okay, and this kind of goes along with that second one. If Kc is really small, we can actually say, well, the forward reaction has hardly proceeded, so we can assume the equilibrium concentration of the reactions are approximately equal to their initial concentrations. So we've got this one. The thermal decomposition of water has a very small value of Kc. It's 7.3 times 10 to the negative 18. So if the initial water concentration is 0.1 molar, calculate the hydrogen concentration at equilibrium. So again, we'll do our ICE thing. Okay, rather than rewriting the equation, I'm just going to do this. Okay, so I know that water is 0.1, and they don't say it, so we can assume that these other guys are 0. Okay, that means we're going to lose some water. Notice the coefficient 2, so minus 2x plus 2x, and just plus x for oxygen. Okay. Well, our Kc expression would be hydrogen squared times oxygen over water squared. And here we're going to say that the initial concentration of water is more or less the equilibrium concentration of water. So we're not going to worry about this 0.1 minus 2x. We're just going to call it 0.1. Okay, so here's where we're just going to call it 0.1 squared. All right, and we're going to use our math skills. Okay. So what I'm going to do, I'm going to multiply both sides by that 0.1 squared. So 7.3 times 10 negative 20 equals, that'll be 4x cubed, so divide by 4. And then I'm going to take the cube root. Oh. There we go. Alright, so x is 2.63 times 10 negative 7, but we want the hydrogen concentration, so that's 2x, so multiply by 2. And you can see it's incredibly small. Alright, there you go.